The most popular example is darts. Why is darts so popular? Darts is very popular because of the simplicity of the model itself, right. So, we are going to assume that omega xy is some circle, and for the lack of anything better, say if we do not have any other circles or any other anything else to use as a yardstick, you might as well have origin center and radius equal to 1, unless there is no other as I said, no other yardstick, no other measuring device is used alongside this, isn't it. So, you can always set, if this is the only thing going on, which is what we are going to assume here, centered at the origin and radius equals 1. If you so want, you can generalize it to have some arbitrary radius r as a parameter, but let me not do it right now. Or maybe no, okay, let me say radius is r, why not? Let me say radius equal to r, just for, because otherwise you know, it's some formulas will use r, and that will be more right. The role of the r will become clear. Okay, let it be r. Some capital R so that you know it is a constant. So, in other words, what we are saying is that we are going to pick points at random only from this circle. This is the point r comma 0, this is 0 comma r. We are never going to pick any points outside the circle. We are going to pick points only from here. How are we going to pick points from here? You are going to stand up there and throw a dart, and hopefully it will never go outside, it will go only inside. Are you good enough for this? We do not know. Okay, fine, that only is omega x. What about fxy? What is the simplest model that you can think of? A uniform value for all of omega xy. The simplest fxy I have to say it is 1 by pi r squared. Let me just say, right, why do I need 1 by pi r squared? This circle, right. So, in this case I could have used omega itself, but I am, as I just said somewhere out there, we are going to keep the generality in mind and always use only omega xy rather than say, okay, you know, it is only r squared, so it is enough for me to use omega. I do not want to make exceptions like that, so I want to uniformly use this omega xy for the region in which they take probable values. So, everybody agrees this is the simplest fxy. You can't have anything more simpler than this. What does it mean physically? It means that you people, when you throw, you are likely to, right, pick any point on the inside the circle, arbitrarily close to the origin and arbitrarily far close to the edge also. So, this model has been used to describe a novice player, where, right, the player has not much control over where the dart lands. So, so regions around the origin do not have higher probability compared to regions closer to the edge. You can debate the usefulness of this model, but as I said, right, it's just an example at this point. If you want to use a more complicated model, fine, do it, right. Okay. Another byproduct of using this model is what? A certain region of some area has the same probability no matter where that particular region is located inside the circle. So, if I take a certain, let us say, small square out here, right, of some area, and I take a small square out here or whatever of the same area. So, same area means same probability. And what is the probability? It's just area multiplied by PDF, because PDF is constant. The integral reduces to just multiplication of the PDF value and the area of the region D. So that is true in every case of constant joint PDF. In every example of joint PDF, the probability calculation cannot get any simpler, because it is regardless of the overall shape of omega xy, for any region which is entirely inside the omega xy, the probability of that region is very simple to calculate. If this region lies partly in and out, well, you only have to take the portion that is inside, that is also obvious. So what are we going to say here? Fxy is not only is it 0, by domain extension you have to put this. At all, right? So the last time I am going to write it, but let me just write it at least once, so that you know that this is part of the definition. So you can include, you can put some square out there and say, well, only this part will count and this part fxy will be 0, so it will not give you any probability. Fine. Okay. So you can see in this example how messy it is to, for example, to specify joint CDF. What would be the, if you pick some point out here, say for example, this point is probably easy, right, not one of the more difficult ones to look to find a joint CDF, but if I pick something out here or even here, you could see that the dependence on this area on this point is very complicated in general. It is not easy. Even here it is not so easy. So joint CDF is automatically I do not have to emphasize this anymore, very messy. Only some values you can easily specify the joint CDF. For example, what is the joint CDF with the origin? 1 by 4, and the joint CDF here is what? Half. Joint CDF here is also half. These are the only 3 points I think where you can write the joint CDF exactly without any calculations at all. And of course the joint CDF will become 1 once that semi-infinite region completely includes the omega xy. Okay. So so this we will come back to later, just keep this example around. Maybe I will keep it here for the rest of this today's lecture. Now there is not much more we can do right now without covering a little more of theory. So let us continue with the marginal PDFs in general. We already said that x and y are continuous random variables to begin with. So they must have an independent existence, independent PDF on their own, without having to worry about the joint all the time. So how are we going to go from joint to marginal in this case, in the jointly continuous case? So what term are we going to use when we are defining omega xy and fxy and so on? We are going to use the term jointly continuous to describe them, which means automatically they are individually continuous as well, right. So jointly continuous xy implies that x and y are also individually continuous, and therefore their individual statistics are very important. In the discrete case, what did we do? We added, right? We drew a straight line for some x, we looked at all the points that lie on that line and we added all those probabilities. We got the what did we call it? We called it marginal PMF, is it not? So what do you think we should do here? What should we do here? Integrate. So, but before that before doing an integration, right, you have to freeze what is omega x and omega y. Where do these random variables live individually? So what do I mean by? So first determine so if I have some arbitrary singly connected region similar to that but not exactly that, omega x and omega y will be the maximum how do you call this, the maximum spread of x and y, which includes all of omega x y. Why is this important? Because here for example you know that capital X, both capital X and capital Y will take values in what interval? Only minus r to r, right? You have to determine that. It need not be as symmetric as this. It is a very nice symmetric situation because we put the origin plumb in the middle. If we did not put a origin plumb in the middle, it is not going to be so nice, isn't it? So in general your omega x and omega y is a maximum spread, if you will. It is a very unscientific way of saying it, but I do not think I put on a better way of saying it out here. Anyway, the picture explains it. Right? If you have some, unfortunately this figure also is very symmetric, but if I took some non-symmetric thing like took some non-symmetric but it's bounded by straight lines, if this is my, right, so this would be the spread of x and this would be the spread of y and so on, right. I do not think we need to spend too much time on this. Essentially omega x will determine both of these without any reference to probability. You know where x and y jointly take values, you know where they also individually take values. It is as simple as that, right. Now what you do is you freeze, let us say you want to calculate fx. What do? You pick some x in omega x, just like we did in the discrete case, right. You draw a vertical line. So let us say you want to calculate the PDF of x at this point. So you draw a vertical line with width delta x. So how are we going to? We are going to use the fact that fx of x is basically a limit, well we will first write probability. Can I hope this is, I think it should be, you can always do this, and then this limit delta x this is not a strong mathematical statement, it is just that if you know what will happen here is this x will dx will cancel, and so in a way it is okay. I mean we can write this, it should be written properly. I may put lim here. So it is a limit as delta x goes to 0 of this ratio, that is fx of x, just by standard arguments. That is the meaning of a density function, is it not? Exactly as we had in the 1D case, there is no difference. There is note that this small x is a fixed number as far as all that operation is concerned. So the entire operation written there, small x is a fixed number, delta x is also some fixed interval. So what is varying here? You are varying y from here to here. The limits of the variation of y are determined by omega xy, but all books will say integrate from minus infinity to infinity if you see books. Unfortunately that does not tell you much about how to apply it in any particular case, so I would term it as some kind of intellectual laziness, right. It is intellectually lazy to write y varying from minus infinity to infinity, but that is the way in which it is written. But anyway, so what is this so to calculate this numerator turns out as a nice aligned rectangle if you do not worry about the starting and stopping points. So what is this p of x, the numerator p of this probability that x is in, x takes values only in some x to x plus dx, right. So what is basically, if you use that formula which I erased, the integral, basically you integrate, you start with fxy, you assuming of course you have the joint PDF, right, you integrate over y from some y1 to y2 which depend. So, we should write the y1 and y2. We should not be intellectually lazy, we should not run away from the fact that there is always some y1 and y2, and that y1 and y2 will depend in general on the value of x you pick. So, I should in general be prepared to write y1 of x here, y2. This is just one example. I mean, I can have multiple such intervals also. If supposing I have a bunch of disconnected regions for omega xy. This is where I have a single region. That is why the books run away from this talking about this all these possibilities and immediately write minus infinity to infinity, very convenient, right. But so supposing here we have a y1 and y2, a single y1 and a single y1 which is the smallest and single y2 which is the largest. Then so this only worries about this, then you have to integrate over x from right, and I should not put okay. It's better to not put x here, I should put some u something, integrate du. So, this is the inner integral, the outer integral is from what, u equal to let us say x to x plus dx. Never reuse the variables, I hope you are all aware of that, right. You should never reuse the variables inside and on the limits. You have enough letters in the English and Greek alphabets to right at your disposal. So, do not ever put x dx here and put x and x plus dx out here. So, if you do all this, what do you get? If you assume that this fxy does not vary much as you go from x to x plus dx. So, what will this is right, this integral will stay as it is, except that it will become right, if this is constant over the variation with x. So, this will be basically roughly equal to this integral y1x to y2x of fxy x comma y dy, the whole thing multiplied by dx. Can I say this or not? Now I can put x in, because I am integrating over only this, I am putting that value of x in here. This number as a number does not change for any, let us say for all values of u, it is if it is the same number, that is what I am saying. This number does not change when I vary u from x to x plus dx. So, it sort of comes out and all I have is integral du from x, right, and what is the value what u am I using? I am using x. Of course, I could say I can use any number between x and x plus dx here, but that makes it unnecessarily complicated, and ultimately I am going to take delta x going to 0. So, I might as well put x there, is not it? In the limit as delta x goes to 0, or sorry, this dx goes to 0, I have to put x only, I cannot put anything else here. So, this is just going back to how double integrals work, is not it? So, what is the fx of x in this, find the limit? So, if you do all that, if you divide off by dx and take then the dx goes away, so the limit can be peacefully taken without any repercussions whatsoever, it becomes what? So, the bottom line is you get this very important expression, the marginal PDF of x to calculate this, right, the marginal PDF. So, it is basically the integral y1 of x to y2 of x, I am keeping it here, of fxy, the x that you are interested in, comma, and you are integrating over y. So, it is very important here the notation, right, the x is the value for which you are evaluating the marginal PDF, the y is a variable of integration. This y1 to y2 is what in books you find written as minus infinity and plus infinity by domain extension. So, to make the formula most general, make it most general, right, most general, set y1 of x equal to minus infinity and y2 of x equal to plus infinity. which is also so hide all the details under the carpet. That's another way of thinking about this, isn't it? Now none of the messy details about what omega xy is or anything, just simply hide it all. This is the way you find in books. So you have to understand, right, that is when you go look at that formula in the book and what is it really saying? It's basically exactly saying this. And this is the idea which will keep coming up a lot when you deal with continuous random variables, right? Even 1D, not just 2D. Because what is the ultimate meaning of a density function? It's exactly that. You are evaluating the probability in a small interval divided by the length of that interval and taking the limit as that interval goes to 0. That is the meaning of a density function with one variable. Is this clear? Everybody, you all understand this? At least whoever is here. I can't worry about whoever is not here, but at least the ones who have come. Okay, so what about y? It's exactly the same thing, right, except you are going to think of horizontal strips instead of vertical strips, and I'll keep that there, and maybe I'll move it and write it here, which implies that Fy of y is basically, again we'll put this minus infinity to infinity in quotes, because obviously this cannot be smaller than minus infinity, and that cannot be larger, right. So you pick the most the case that includes everything and anything and put it there, Fxy. This unfortunately the thing is, this looks very innocuous, but it's, you have to realize which is the variable you are integrating over now. What should we put here? Dx, right, you are integrating on the horizontal direction, keeping y fixed. So this is very analogous to what we did in the discrete case. In the discrete case, you get the PMF of y, you drew a horizontal line and you looked at all the points on that line and you added all those probabilities. So here you have to do an integration. By identical reasoning. Okay, now the reason the nice thing is to have this up there, right. So apply this, all of this to this. I will remove this. So once again, I think the importance of first determining omega x and omega y cannot be emphasized. You need to, right, first thing about a random variable, please think about what values it can take. Any derived or what otherwise, right, that which is not straight away given to you, first thing always should be what values it takes. So when you apply this marginal PDF calculation to that example, what do you get? For the darts case, the simple model, I guess I said all about, and I don't want to put stuff about it, novice player and all that. Well, you can write it down, of course, but anyway. So in future, let me also say we will use novice darts as a simple shorthand for all of this. So darts PDF for a novice player, right? You know VIC, novice. Okay. So because I can't keep writing this all the time. Okay. Okay. So for this example, what is Fx and what is Fy? Somebody do the calculation. Tell me. What is Fx? So if I pick an x here between minus r and r, what will be the integral? So this is 1 by pi r squared into dy. What are y1 and y2? Minus r squared minus x squared to, what is the value of this integral? And automatically 0 outside. So this is your omega x. Note that this is not a uniform PDF anymore automatically. So it has far higher probabilities of taking values closer to the origin than at the extremities. That should be obvious from here, right? If you say any point is equally likely, obviously the x coordinate of that point is more likely to be close to the origin than minus r and plus r, right. So this outer boundary of the circle is a very artificial construct in this case. Somehow suddenly the point probability of a dart landing here is something, and then outside it is 0. So in a way it's unfortunately it's not a great physical model. Maybe if you take r extremely large it might become better, but then if you say if r is extremely large then this is not going to be that physically meaningful. But anyway, it's a marriage of right not so physically meaningful ideas, but we are living with it because it's so simple. By symmetry, what can you say about the marginal PDF of y? It's exactly the same, and fy of y I can just say is fx of y without any, right, without rewriting anything. Note that fx, right, you can use any argument. I do not have to say, right, there is no there is nothing, no rule to say that this must be the uppercase letter, this must be exactly the same lowercase letter, nothing of the sort. So what is the meaning of this statement? This statement says that x and y are identically distributed, they are ID. With the same statistics, the same range, the same PDF. Just summarize what we did. So we started with omega xy fxy, then we have shown how that model can be used to calculate first of all any probability by integration. Remember always, right, that the the joint PDF has to have unit volume, otherwise it is not properly normalized, it should, right. So that again I did not write it out in the beginning of this class, but remember joint PDF always has to be normalized to unit volume. So in this case one more thing to remember is probability is volume. One more way of remembering this joint PDF thing, right, you have a volume here. Then that is what we did first, and then we took up this example and we showed how in general you can go from joint to marginal, very similar to, or in an analogous way to what we did for discrete. But you cannot go from in general from marginal to joint. Supposing I gave you those two PDFs, how would you, right, in your wildest day, this is mathematically impossible to do, right. You cannot say that just given this PDF here for x and a similar PDF, identical PDF for y, that this must be the joint PDF. It is not possible. Somebody can say no, and they would be right. So when is it possible to that the marginal and joint are equivalent ways of describing the situation? That requires independence. So in general random variables are never independent, they are always dependent. Right? Independence is a very special case, remember.